I met Christopher in my optics class last year. He was one of the best students in the class. He was most attentive and hardworking and one of the smart students. So I had an eye on him. And after the class is over, I offered him whether he is interested in one of the research project called Electronic Speckle Pattern Interferometer. This is a very powerful interferometry and practical. So this is a technique that allows you to visualize the sound. There was a couple of speakers talking about the sound. They talk about how to hear the sounds and pitch, things like that, but you can actually see the sounds. So I offered Christopher whether he is interested, and then he was excited. So that's how we started doing the research project. In fact, this is not the first time that we did the ESPI project as a capstone. We did it about 2 years ago with another student, but we didn't really go too far. We spent most of the time just in preparation. But this time, in second time with Christopher, we now have a working system. And I believe that's a really big deal because we know from theory how this ESPI works, but in reality, to make it happen in practice is very difficult because anything can go wrong. In fact, during our project, at the beginning we used the wrong laser and the lens was not right, and then polarization wasn't right, and then to figuring out it was like going through the minefield. But during the project, I try not to intervene too much. So whenever the Christopher stuck with a problem, I just let him suffer and struggle. I try to give him the minimum guidance, and until he figured that out, and he actually did. So I'm really proud of him, and I would like to call this as his first victory as a researcher, and then I hope he continues in the future. So let's invite the speaker and then enjoy the talk.
Thank you, Dr. G, for that great introduction. As he was saying, I've been working with him over the past year on electronic speckle pattern interferometry. So, as a brief introduction, electronic speckle pattern interferometry is a method of detecting surface deformations by shining laser light onto it, and specifically the outer plane electronic speckle pattern interferometer is sensitive to this. And that allows for the detection of small surface vibrations and deformations. And one of the examples of the surface vibrations is right here. This is an image I got off the internet, and this is a vibrating plate at 924 hertz at one of its resonance modes. So this is a standing wave pattern that's created on the plate, rather complex. But one of the actual more practical applications is when you shine this laser light on something like an aircraft rotor right here, you can see really small surface defects in the aircraft rotor. So in giant aircraft wings, you can just have a laser beam, use a beam expander, and then just illuminate the whole aircraft rotor, wing, or whatever, and be able to see these small defects on the scale of 1/2 of the wavelength of the light used. So you can get it down to like a few hundred nanometers, and it's a very powerful tool for this reason. But one of the areas of interest that I was focusing on is seeing how when you have these vibrational modes, yes, you know that you can detect directly the surface deformations, but what about little non-uniformities in the actual material you're looking at? Like if you have a thin membrane and you're vibrating it, what if it's not completely uniform? Can you see a difference if you compare that vibrational mode with a standardized case? So before I dive right into my research, I want to give you a little bit of a background on the theory behind it. So the most basic thing that is underlying all of this electronic speckle pattern interferometry is interference. So the number one key thing in this is that light is a wave, and like a water wave, it can interfere with itself. So you can have constructive and destructive interference of a light wave, and one famous example is if you have 2 point sources of light right here, and you can have them interfere on a backstop, and you'll have constructive interference when the peaks and peaks, or troughs and troughs overlap, and then you'll have destructive or dark interference when a peak and a trough match up, and they'll cancel each other out. And that's famously given by this equation right here, which is the one of the most notable, or the most utilized equation for interferometers, and you pretty much have the intensity of the first beam right here, plus the intensity of the second beam, plus this interference term, which is dependent off of this delta right here, which is the wave vector times the path length difference between the two waves that are traveling. And that will give you the general intensity seen on the backstop. So the next concept is the concept of speckle pattern. And this is a really neat consequence of having coherent light source hitting a rough surface. And I actually have a little bit of an example right here. When you look at that, you can see that there's this speckled surface, so it can get a little more stable, on the wall. And if you move your head back and forth, you'll notice that the pattern moves with your head as opposed to just like staying stagnant. And that's because, as you can see from this diagram right here, you have a bunch of rays hitting a rough surface and then they'll be reflected in multiple directions. So let's say you have one coming from right here and then one coming from right here and right here. So they might constructively or destructively interfere based off of how long the path length difference is for them. So if you put a wall up or something like that right there, then there'll be constructive, destructive interference. If you move it back a little bit more, the pattern will change. And the same thing is true as if you just have, if you're standing right here and if the wall's moving, the speckle pattern will change. So the individual size of each one of the speckles is given by the Rayleigh criterion. So pretty much like the angular separation is dependent off the wavelength the light used divided by the diameter of the aperture. So if you, again, if you look at this pattern and if you squint your eyes, you'll see that the pattern gets bigger. And the speckles will get a little bit bigger. And that's due to you changing that D on the bottom. You're making the D smaller so the angular resolution gets bigger. So that's one little parameter that we utilize in our setup. So to create a speckle pattern interferometer, which is the first step to full ESPI, you generate a speckle pattern and you initially split the beam. So you send one beam through a beam expander and then illuminate a wall like with this. And then you have another reference beam, just like a typical interferometer, and you image the system with a lens, with essentially a camera. You create a one-to-one mapping, and when the beam is being converged again, you recombine it with that reference beam. And what essentially happens here is each one of those speckles right here becomes its own interferometer. So each one of those speckles that I showed you on the wall has its own interference pattern. So it'll cycle through a bright-dark cycle every half of a wavelength that's experienced. So this is a really, really nice consequence of the speckle pattern because you're able to get an interference pattern that you can actually use from regular objects. You don't have to have stationary mirrors like with LIGO or something like that, giant mirrors that have to move one way or the other, like a Michelson interferometer or even Mach-Zehnders. Like, this is used on everyday objects and you can get real results from this. And again, it's given, each one of those speckles is given by this interference term right here. So when it becomes an electronic speckle pattern interferometer is when you take two images. One image is, let's just say this wall is stagnant right here. You take a picture of that on the CCD camera right here. And then let's say this wall starts moving. So it might be oscillating or you just displace it a little bit. And then you could imagine that the entire speckle pattern will shift. So things that used to be bright, the speckles that used to be bright might be dark or vice versa. So depending on that displacement, you can say, okay, I'm going to take the image of the vibrating surface and I'm going to subtract the image of the reference surface. So you'd be able to see any differences that happen throughout the speckle pattern. And this is where it kind of gets a little hard to see. I don't know if you can...
Should we cut the lights?
Yeah, can I?
Yeah, hit D.
Marissa, yes, I think has it in the back, right?
D for duh.
It's just the one in the front makes a difference.
Is it same? No?
We can make it worse.
A little bit better. Yeah, you can still kind of see it. And there'll be bigger images later, but you can see it. Oh, there we go. All right. So you see right here, this is a vibrating surface and this is a reference surface. And just looking at both of them, you really can't see any difference between the two. But when you actually subtract the two, and then when you do a little bit of image processing, like enhance the contrast, do some edge detection, you're actually able to bring out this really cool pattern of the surface. This is a standing wave created on the surface of the material, and this was specifically like I'll show you the picture later, but it was a square membrane vibrating at something like 1.3 kilohertz. and it creates this nice standing wave pattern that you can visually see just by shining laser light on it and then just doing a little bit of a basic image subtraction on it. And then just kind of for anybody that wants to know, this resulting image is given by this function right here, so it's pretty much dependent off the Bessel function, and then this right here is just the path length difference, this delta z term. And so this has been the focus of most of my research right here, is that getting these images and then seeing how we can alter the vibrational wave patterns by altering the symmetry of it. So the setup that we have for the ESPI is we have this laser that expands the beam through a beam expander, and then it has this half wave plate here because you have a polarizing beam splitter, so you would have the horizontal polarization being transmitted and the vertical being reflected. So if you orient this half wave plate, you can vary how much is going through the polarizing beam splitter and how much is going and being part of the reference beam. And you want to, ideally, you want to have as much going to the target and as little to the reference beam as possible, just so then you can get a maximum intensity, since this is going to be, most of the light's going to be scattered right here and kind of wasted when it hits the target. So then you have the image, so this whole system right here is essentially that camera that I was showing you. You got the CCD, you got the beam splitter, and you got the converging lens. And then you have an iris right here, so then you can change the diameter of the aperture, so you can change the speckle pattern, or the speckle size at the same time. And when you recombine the light, it's just like the speckle pattern interferometer, and then you have it recombined with the reference beam onto the CCD camera. And then you just image it and put it into an imaging processor. And this is just the actual setup we have. Here's the laser, beam expander, half wave plates, polarizing beam splitter, converging lens, beam splitter again, and then CCD. So the target that we had, this is just a very basic cartoon of the idea that we were using for it. So you pretty much have this movable membrane, which is, right here, this is just a frame, this blue part, and then this is like a piece of paper, let's say, and you have a stick attached to that membrane, so to the middle of this piece of paper, and you have a speaker hooked up to that stick. And then the middle of the stick is in the middle of the membrane of the speaker, so then you can just attach the speaker to a function generator and then apply a voltage and generate a sinusoidal wave, so then you can have different sounds, different excitations, so then hopefully you can reach a resonance frequency of the material and get a standing wave pattern. So some of the initial results we got, this isn't exactly the target I was showing you, this is just bottom of a paper cup put over that speaker and then just kind of taped so you have it fixed. But you can see right here that you do have circular patterns kind of originating outward from the center, which is what you would expect if you were just kind of moving the membrane in and out. You expect it to kind of go out in concentric circles with the shape of the membrane, unless there was some sort of symmetry alteration, like in this image where I cut out sections of this cup, and then you would expect it to, again, kind of go out circularly right here, but then when it starts hitting these sides, you would expect it to kind of deflect. And that's exactly what you're seeing here. So this is a confirmation that, yes, altering the symmetry of the cup does change the vibrational mode of the, or vibrational pattern of the standing wave, and that the methods of detection from the ESPI are good enough to be able to see this. Now, one thing that I'll also say, you'll see these strange diagonal lines. This has to do kind of with what Dr. G touched on. We have like these, this problem with the lasers, like it's mode hopping a bunch. So these diagonal lines are present in all of the images, but if you didn't have any mode hopping and they were stable, you could just subtract them out and you wouldn't see them. But because it mode hops, they shift slightly. So when you do the image subtraction, they come up here, and they're going to be present throughout the rest of the slide. So might as well touch on that now. So these are further results. This is just that square target that I was showing you, and then there's that pattern that I showed you originally, and this is just the bottom left-hand corner of the square target. And you can see it kind of loses interference, and again, that's due to the mode hopping of the laser. But this one's kind of interesting. This kind of led me to believe that the tension on the paper target wasn't completely uniform, and there might be some sort of like flopping motion in the vibration of the target. So that kind of brought up a red flag when I saw that. So I tried to readjust it and get the tension down a little bit more. So all that stuff's pretty cool, but at the same time, like, doesn't have too much of a practical application. So one thing that I decided to do was, well, what if you have this target here and you just have a perfectly uniform piece of paper, like just as a basic example, and what if you alter the symmetry of the paper without like putting a hole in it? So what if you scrape a little bit off the back and then take a picture of the vibrational mode beforehand, scrape a little off, see what it looks like afterwards, scrape a little more off, and see, well, is there any way that you can correlate the change in the vibrational mode pattern to the way, to where the non-uniformity was in the paper? So that was kind of my idea for this semester, is can I do something like this to just see if there is a change like that, because that could have some sort of implications in the industry for more thin types of material that you can't apply stresses to, or you just can't like scrape a hole in, or you're not too worried about that. So some initial results of this, like, they were actually rather encouraging. I actually, right here, I don't know if you can see it, there's a lighter contrast area where that's corresponds to right here on the target, and about right there in all these images. And that's where I took the razor blade to it. And so this image, this was just unaltered. This is just standing wave pattern, and these were taken at 1.357 kilohertz. And the reason I chose that is just, that was a higher order resonance mode. So you had more like more nodes forming on the actual piece of paper. So I was hoping that this effect that I'm going for might be a little bit exaggerated the more nodes that you actually have on it. So this is the standing wave pattern that we originally got. It's not perfect, as you can see, it kind of varies with time, but it was as close as I could get. So then from this picture to this picture, I scraped off a little bit of the material on the back of the target. And you can actually see here that there's it's very slight, but this part right here, this is right where I scraped the material off of. This one, it's almost like circular at the tip. And then here it becomes pointed. And I was actually able to take measurements, and these measurements right here are based off of the longest dark region in that, so like the longest non-moving part of this pattern. So the horizontal length of this one, so measured this way, was 7 millimeters, but then from this one to this one, it increased to 9.5 millimeters. So there's an actual physical change in the length of that little part of the pattern. And then when I removed even more material, you can see it becomes a little slightly more elongated and a little bit fatter at the tip. So this at the very least shows, yes, there is an actual effect when you scrape off some of this material from the target, and you're actually able, there might be a way to be able to directly correlate and say, oh, this, like if you had a standardized case, like, and you just knew, okay, this is a perfectly uniform piece of paper, and then you had some, or piece of material, and then you had something else that was questionable about the uniformity of it. If you compare the two, and then there's very slight changes in the vibrational mode patterns of the same frequency when it's under same tension, then you might be able to say, hey, it looks like there's a non-uniformity. Maybe it's a little bit thicker right here, a little bit thinner, something like that. And so this was just the result of one test, so I wanted to kind of confirm the results in this next one. So I just took another 2 images right here. This one is I had the same exact target setup as before, and I just swapped out the piece of paper for a new one. And this one is the vibrational mode pattern at 1.572 kilohertz, which was the standing wave that I was trying to go for. Again, it's not perfect, but it was as close as I could get. And right here, instead of removing, like scraping it off, I almost put more lines in it this time. And you can see like it completely like changes the vibrational wave pattern there. So I mean, kind of, this one is making it seem like, depending on the way that the symmetry is altered, it might make it a little hard to see exactly where the non-uniformity is in the material. So at this point, this is where I would want to continue doing experiments like this, like change out a new piece of paper, maybe swap up some shapes, and then see what these targets look like when you have different vibrational, like different more complex vibrational mode patterns. But unfortunately, I didn't have the time to do that, just because each one of these images took like 2 hours to get just this quality due to the mode hopping in the laser. So I wasn't able to get that. So in conclusion, I hope that you can leave from here knowing that the ESPI is a very powerful tool, and it's used in the industry a lot for, like I was saying, aircraft rotors and detecting small surface defects. And unlike most interferometers, one of the most valuable aspects of it is that you can actually shine it on everyday objects and be able to get results in interference patterns from this, and that makes it so then you don't have to have it in a strict laboratory setup. Like the setup that I was showing you, it can be condensed to a little breadboard, and then you can just take it around, and then you could like shine it at this wall if you wanted to, play an acoustic speaker. And then one thing that they do is they, archaeologists have been starting to do that. You put a speaker right here, and you play some sort of acoustic noise, and if there's a resonance behind the wall, you'll be able to see, okay, the wall's being slightly displaced right here as opposed to over here. There might be a cavity behind this wall. So there's a lot of small applications that has been applied to more and more, and the more that it gets more compacted as laser diode technology gets better, and you have, as long as you have good enough optics, like you can, there's a lot of things that you can do with the ESPI. And as I was saying, if you combine this with vibrational analysis, it might be possible to determine non-uniformities inside of different materials, like the thin sheets of materials. And then that would make it so the ESPI has uses through, like, in a very wide range of the industry, from aircraft rotors to very thin sheets of materials, and then to like bricks of steel, where what they're doing is they're getting an in-plane interferometer, drilling a hole in it, applying a stress, and then using stress strain analysis on the material. As you can see, the in-plane kind of move. So that if something like this worked, it could actually kind of bridge a gap between the pure out-of-plane detection of deformations and the stress analysis of it. And finally, I would like to thank Dr. Sang-Yong for helping me so much throughout this project, Dr. Shi for giving me input throughout the presentation process and capstone presentations, Steve Anderson for providing the laser and all the optics, and he's honestly helped me a bunch when Dr. Shi, like Dr. G was saying, when he let me on my own and like deal with the problems. We go, Steve, can you help me? And he do everything he can to help me. And then I would like to thank Dr. Severson for letting me mess up the little corner of his optics table for an entire year. And then Dr. Jeremy Qualls for printing my 3D frame for the square target that you saw there.
Sweet.
Thank you.
Now it's open for